Okay.
Should be okay.
Oh, okay.
Yeah.
Hello and welcome. Thank you for probably taking a step out of your comfort zone and coming to this talk. I'm basically going to prove to you that it's not too different from computer science after all. Similar process, different things that we're looking at. So I guess sorry to anybody who has more than a cursory understanding of the things I'm about to talk about. I've written this for an audience of computer scientists and software engineers who probably only have a vague memory of high school level physics. So as such, I am going to avoid mathematics wherever possible. However, in this particular talk, I have included one proof, but it should be pretty easy to follow, hopefully. My aim with this talk is to explain the techniques that observational astronomers use to probe the universe, otherwise known as how we make electromagnetic radiation our bitch, hence the title, and how this relates to my own research in cosmology. This isn't relevant yet. Okay, so the main way that we do this is through light spectra. Humans all around the globe and throughout time have looked up at the sky and tried to make sense of the universe and our place in it. Honestly, just look at the Milky Way without any light pollution. Is it any wonder that we used to think it was the playground of the gods? Like, it's awe-inspiring. But we have got so much better at it. Modern astronomers aren't much different, except now we have a lot of cool telescopes, cameras with CCDs, and the ability to put them on the other side of the sun. So this here, I have a pointer, sorry, give me a second. This is the electromagnetic spectrum. The first step in our quest to understand modern astronomy is to look at the electromagnetic spectrum. This is from the 2015 edition of the Encyclopedia Britannica. It's a wonderfully simple diagram, kind of, that shows all of the pertinent information that we need. Depending on your experience in education, this may be intimately familiar or completely foreign to you. Something I do need to clear up, I will be talking about light or radiation as simultaneously both a wave and a particle, because it behaves like both. This is the wave-particle duality. You don't really need to understand the differences, but if I talk about a photon, it has all of the properties of a wave. So you can see here, it has a frequency, it has a wavelength, even though it's actually a particle because it has a defined amount of charge, all of that stuff. As Wherein said in his previous talk, it's all about abstractions. This is an excellent example of how all categories and abstractions are just simply human constructs. The only thing separating the things on this list are the amount of energy that the photons have. So, how is electromagnetic radiation created? Buckle up, folks. Quantum Mechanics 101 is incoming. This is a diagram of a hydrogen atom. It does not have a nucleus. I am sorry. I made this very, very quickly. This is the simplest of all of the elements, represented with the planetary, otherwise known as the Bohr model. Whilst the Bohr model of the atom is not the most precise or the most accurate that we have, it's perfectly sufficient for this purpose. Now, something you need to know about us physicists, we are very fond of using the simplest model that fits the data that we are examining at any given time. You may know that an electron shell is technically a probability distribution of where you'll likely find an electron at any given time, but it provides a level of precision which is rather unnecessary for this particular purpose. This is why the Bohr model is still taught at secondary high school level physics and chemistry worldwide. It's good enough for most purposes. It's truly exceptional for understanding chemical bonding on a conceptual level. So how does this relate to electromagnetic radiation? It's quite a simple concept. Electromagnetic radiation is absorbed and released when electrons move between these discrete energy levels. So this is a diagram of absorption. So this electron here is absorbing some light that's coming in here. Oh, it's nice having a wave. Sorry, I'm a bit distracted. It absorbs a photon and it gains energy and it jumps up here. So when it absorbs this photon, suddenly the electron has too much energy to exist in this lower shell. So it jumps up to another possible energy level, which is labelled as E3. When this happens, the electron is now in what is known as an excited state. This is considered unstable, and like all of us, electrons just want to be stable. So what do? They want to get rid of this extra energy so they can go back to being the lowest available energy state that they can possibly be in. To do this, it must produce a photon to rid itself of this additional energy. This is how electromagnetic radiation is created. This is called emission. It lets the photon out. Pretty simple, really. Each of these transitions corresponds to a photon with a specific energy. The difference between the two energy levels equals the energy of the photon. This can also, the difference between the two energy levels is the same as the photon. It can be also calculated as the product of the Planck constant and the frequency of the corresponding wave. That's HF right here. So basically, it absorbs a photon, it lets it out. The photon will always have the same amount of energy depending on the transition that is taking place. However, it's often more useful to know the wavelength of the light. And these two are equivalent. You basically get rid of the frequency, you substitute speed, distance. Speed equals distance over time, essentially. Where c is the speed of light in a vacuum. So let's do an example. I told you there would be a little bit of math. This might look scary, kind of is, but it's really simple. So let's consider the transition between shell number 3 and shell number 2 in a hydrogen atom, like was on my diagram. And this corresponds to radiation in the visible part of the spectrum, specifically red light, of a wavelength of 656 nanometers. The energy of the transition is given in the general form shown here. So for any transition, we can work it out using that formula. The value of this constant is based on this constant here. Is based on the premise that the nucleus of the atom emitting the radiation is exceedingly massive compared to a single orbiting electron, hence the infinity symbol. You can work it out here. So this particularly refers to the mass of the electron, that is the charge of an electron, 8, permittivity of free space, Planck's constant, speed of light. Every element has a different atomic number. That's what defines which element you have. It's the amount of protons that are in the nucleus, which means that this constant is ever so slightly different for each element. It's easy to calculate in the case of a hydrogen atom because there's only one proton and one electron. But this is basically a mechanical two-body problem. One way we can simplify these problems in classical mechanics is to calculate the ineffective inertial mass. This is what is meant by the reduced mass, which that's what these correspond to. For the Rydberg constant of hydrogen, we can use these reduced masses to work out the scale factor of our infinity, which is very, very little. There's like 5 nines before it changes, so it's very, very small, but it is significant. So we can work out, I did all of this math off screen. I thought it might bore you if I did it here. But essentially, the energy associated with this transition is 3 times 10 to the 19. So we can use that. We can work out the wavelength, which is 656 nanometers. Like I said, you don't have to take my word for it. This formula applies to every single energy level transition that can occur. The law of the conservation of energy means that absorption and emission are always equivalent. Energy in must always equal energy out. Each atom or bond in a compound has a specific energy levels that can exist. This diagram shows This diagram shows the absorption and emission spectra of various elements. So you have absorption at the top, emission at the bottom. As you can see, they line up perfectly. each of these serves as kind of like a chemical fingerprint for various bonds that exist in molecules, between atoms. They're everywhere. Thankfully, our wonderful friends at NIST have compiled a massive database of reference spectra so we can look them up. This does save a lot of time, though speaking from experience, isolating a peak in a large dataset, doing the prerequisite statistical analysis to reduce the noise, and identifying them from said database is an absolute pain in the arse, and it can take several days. If somebody wants to automate it, be my guest. An example. So this is what a typical emission spectrum actually looks like in terms of what we deal with as scientists. This is something that I personally made as part of my research at university. It's a composite spectrum made up of 500 different spectra of a particular type of galaxy. Galaxies that have supermassive black holes in their centres, which is most of them. These galaxies were first discovered back in the early 60s. Researchers thought they were stars, but weird ones that emitted radio waves. Our understanding of stars, we didn't think they would emit radio waves, hence the name of quasi-stellar objects, or as we call them now, quasars or QSOs. See, QSO. The name stuck even though we know far more about them now. They are so bright that they often look like stars. It turns out they're both really bright, but also really far away. This sample is made from a bunch that are around 10 billion years old. More precisely, this is what they looked like 10 billion years ago. If anybody wants to get into the details of how this is done from a data science point of view, I'm happy to discuss it at length and share my code with you if you want to play around with it yourself. All it takes is some comfort with Python and a few SQL queries, because all of the data is public. Each of the peaks labelled here represent one of the transitions that I was talking about earlier. It can often be tricky to determine which peak is which, since many transitions have similar energies. Some of these peaks are made up of multiple species being present in roughly the same place. There is often as little as, say, 0.2 to 5 nanometer separation between them. These were identified by me fiddling with the code, doing a lot of statistical analysis and staring at my laptop screen so intently that my optometrist would be incredibly mad at me if they found out. And I'm including this for me because I found it really, really interesting. You see these labels here that have the little square brackets. You might not be able to see them very well. They represent something that astronomers call forbidden or semi-forbidden lines. If it has a single bracket, it's a semi-forbidden, and if it has a double bracket, like there is down here with neon, it means it is forbidden. We can see the neon label just here. I coloured it in red as uncertain because it's a bit difficult. I did that to err on the side of caution because when you say you found something like this, people are a bit sceptical. This particular peak represents a transition which can only occur when the density of atoms is incredibly low. What this means is that there was some neon gas, probably, just floating around in the interstellar medium near the galaxies in question when this data was collected. Seemingly enough of it to resolve into a defined peak and not just to be written off as noise. Because you see all of these bits here, they do correspond to peaks, but they are probably things that are in between us because of the way I have to normalize this data. I picked a very narrow range, so as you do the normalization, it shifts things. So you can't really resolve these ones, but I went through and I looked at every single one of these peaks and figured out, looking at the NIST database, which is which, what makes sense, what's possible, all of that stuff. The semi-forbidden lines of oxygen 4 and carbon 3 are similar, except these transitions are about 1,000 times more likely to occur, so it's less controversial to say that you found them. I should have set on the slide. The astronomy fans in the audience, which I'm going to go out on a limb and guess is a fair amount of you, probably know that various space and ground telescopes detect photons in different parts of the spectrum. JWST is looking in the infrared, the Hubble Space Telescope does ultraviolet, visible and near infrared, GALEX did ultraviolet, Chandra focuses on X-rays and the Very Large Array. Yes, astronomers are even better at naming things than historians, focuses on radio observations. This happens because different astrophysical processes spit out photons of various wavelengths across the whole spectrum. The type of telescope you need depends on what you are observing. The dataset I used in the example here was gathered by the Sloan Digital Sky Survey, which is publicly available because public money, public data. It's collected from a ground-based optical telescope in New Mexico with a dedicated 2.5-meter telescope at the Apache Point Observatory. The eagle-eyed among you probably noticed that the wavelengths that are down here actually correspond to the UV part of the spectrum. By the time light reaches us, the wavelength has decreased to such an extent that it's now in the visible part of the spectrum. This happens because of a phenomenon called redshift. We all experience this phenomenon, in a way, every day. Specifically, we are very used to Doppler shifting of sound waves. This phenomenon is why we can identify where a sound is coming from. A sound of a constant pitch seems to change based on your distance from us. This is especially apparent with emergency service vehicles. This is by design, so you can locate them in traffic. But this also happens with light as it travels. For the purpose of this example, I'm only going to explain the relativistic Doppler effect, i.e. the increase in wavelength and corresponding decrease in frequency and photon energy associated with two objects moving apart in something that we call a Minkowski spacetime, otherwise known as spacetime that is completely flat. That will make sense when I talk about it in my next talk. Put simply, the change in the radiation wavelength occurs because the waves are physically stretched out. And we can assign a numerical value to this redshift with this equation. This is a very basic form. There are different sorts. The redshift c is equal to the recessional velocity, so that's how far something is moving away from us, how fast it's going, divided by the speed of light, essentially. This is also equivalent to the difference between the observed wavelength, the emitted wavelength, divided by the emitted wavelength. Because a lot of what astronomers do, we figure out the theoretical basis of what we're actually looking at. So we know lots about a star, we know what should be coming out of it. So we see something, and then it's in a different part of the spectrum. Well, we know that it must refer to that. If I go back here, I wasn't originally planning on explaining this, but this part here is used a lot because these are different transitions within the hydrogen atom. We know that this, which is called the Lyman alpha forest, should always be present if we are looking at these types of objects. So you look for this cluster, and then you shift appropriately. But this also works in reverse. For example, the reason why we know that the Andromeda galaxy is moving towards us is that the radiation from the galaxy is actually decreasing in wavelength. Ergo, Z has a negative value. This phenomenon is actually called blue shift, because we're great at naming things. In the case of Andromeda, Z is equal to about minus 0.0003, meaning that it's travelling towards us approximately 113 kilometres per second. Meaning that it will collide with the Milky Way in about 5 billion years or so. But don't worry, we probably will be extinct by then, so it's nothing we need to be concerned with. Galaxies actually merge a lot. It was far more common in the early universe. This means that we've been able to study them in quite a lot of detail. We think it's the reason for all of the mega galaxies and mind-bendingly supermassive black holes that we see in our data. If you want to look at this further, I recommend a video about the largest objects in the universe by Kurt Kazard. It's amazing. It puts everything scale representations. And also, if you're interested and you're mathematically minded, the kinematics of galaxy systems is fascinating if complicated math is your cup of tea. Though, truthfully, this formula is only an approximation because we don't live in a flat space-time. Not completely, anyway. This formula completely ignores the effects of special and general relativity. However, it is the simplest way to explain the concept, just like the Bohr model from earlier. It is not entirely wrong when considering that space-time is pretty flat, which is general relativity, and most things aren't travelling anywhere near the speed of light, special relativity. Relativistic Doppler shift is, in my opinion, the least interesting of the types of redshifts astronomers need to account for, but I do realise that I am biased. I wrote a whole dissertation on gravitational lensing, and we're going to get into cosmological and gravitational redshift in my next talk. Does anybody have any questions? Did any of that make sense? Okay, if we've got no questions, then that's fine.